In section 6.1, we're actually looking at an application of integration. You know, we've learned all these integration techniques. Well, what can we do with it? Well, one thing that we can do is to find the area beneath a curve. And up until now, the pictures that we found the area of were something like this. We found the area between A and B, between a curve, let's say the curve is named f of x, and the x-axis. So up until now, we would take the integral from a to b of the function f of x dx, and we would call this solution true area because it's all above the x-axis. Now, if some of this area happened to be below the x-axis, then we would say that it was signed area. So basically, we were always bounded below by this line y equals 0. Put that back in, y equals 0. Well, what if we didn't have just that line of y equals 0? What if we had a situation where we had a curve and a line, and I wanted to find the area bounded by them? Like in this situation. Or I could even have a trig function, and I could look at, let's say, a trig function and a line, and I could find the area bounded by them as well. I could also have area below the x-axis. I could have two parabolas, and I could find the area bounded by them. Even though some of the areas above and below, the technique we're using will give us true area. Well, when I'm looking at all these different techniques, again, I'm trying to find area. And the area is equal to base times height. That's what we always need to remember. So area, in this particular case, is going to be the integral of some function, you know, base times height, from a to b. Well, let's look at the picture that we have here to the left. And we can see that these points of intersection seem to be important. So we'll call this one A and this one B. So these are values of x. X equal A and x equal B. Now I need to sum rectangles. Well, up here when we summed rectangles, the height was just f of x because I started off at y equals 0. Now down here that's going to change though because my y-axis, or sorry, my x-axis at y equals 0 is not my bottom curve. So each rectangle will have a height of your upper curve, which we'll call f of x, minus your lower curve. So this height of this rectangle is the upper function value minus the lower function value. So that's going to look like f of x minus g of x. So that's the height. And then this width right here, we're going to call dx. That's the incremental width. And so that's what we're going to do here is we're going to sum these rectangles. Base, which is this value dx, times height, f of x minus g of x. So when I have vertical rectangles, when I set up my limit to find my area, I always take my upper curve minus my lower curve. Always. Now this is if I have vertical rectangles. Let's look at an example where we might have horizontal rectangles. So we could look at a picture like this, and I could say, let's go ahead and find this area bound by this curve and this line. So this area I could find as well, but I'm going to be using horizontal rectangles for this example. Now sometimes you can use either. You don't have to choose. There's not a right way and a wrong way, but a lot of times one is easier than the other. And in this particular case, the horizontal is easier because when I set up my rectangles, you can see that the right curve is always this sideways parabola, and the left curve is always this line. Now if I had gone with vertical rectangles, the curve on to the right of this point is different than the upper curve to the left of this point. So I'd have to set up two integrals here to use vertical rectangles. So horizontal rectangles are definitely the way to go here. Now for this particular graph, I have points of intersection as well, and we'll call the upper one B and the lower one A. So I would integrate from y equal A to y equal B now. We're going to use my right curve to be f of x and my left curve to be g of x. So the length of this rectangle laying on its side is f of x minus g of x. The incremental width, whoops, I already made a mistake. Is that x or y? It should be f of y minus g of y because the vertical value here of my width is actually some incremental change in y that we call dy or delta y. So this is not upper minus lower. When I have horizontal rectangles, I have right minus left. So f of x minus g of x will give me the length, basically, of each rectangle on this axis. And I'm just summing rectangles to find area. So the easiest way to look through these is to go through a bunch of examples. Now on the examples, we're not going to be focusing so much on integration as we are to set up. So for our first one, let's find the area bounded by some graphs. So we'll find the area bounded by the graphs of all of these pieces. First of all, y equal x squared plus 2. That's a parabola opening up with its vertex at 2 on the y-axis. Y equal negative x. This is a straight line that bisects the second and fourth quadrant. X equals 0 is a vertical line that's basically the y-axis. X equal 2 is a vertical line going through 2. So we need to know something about curve sketching to be successful with these, because we have to be able to see what's upper, what's lower. Sometimes we're not going to be able to, but for these we certainly can. So again, we had a parabola opening up with its vertex at 2, so this is y equal x squared plus 2. We had y equal negative x, bisecting the second and fourth quadrants. We had x equals 0, so this is y equal negative x. Here's x equals 0. That's the line x equals 0. And we'll call this the line x equal 2. Now, the graph of x squared plus 2 and y equal negative x never intersect. But let's go ahead and double check that just to be sure, because we will be able to have to find points of intersection for some graphs. The way we find points of intersection is we set the functions equal to each other. So we'd set x squared plus 2 equal negative x. So we'd add the x across. And we see that no matter how we factor this, 2 is a prime number, all my values are positive here. So if it did factor, to get these first and last terms, this is how it would have to factor. But notice here my outside and my inside sum to 3x. So this does not factor nicely. I don't have a point of intersection, I have imaginary roots. So this is the area that I'm trying to find here. This is the area that I'm trying to find. So the next thing I want to know is, should I use horizontal or vertical rectangles? Well, I don't think horizontal rectangles would be a good idea, because as you note here, from this region, this lower triangle piece right here, my right curve remains the same, but my left curve is the line. In this region right here, my right curve remains the same, but my left curve becomes this vertical line. And then in this upper triangle shape, it's a smooth curve here, so it's not exactly a triangle. What I have here is the right curve is the same, but my left curve would be this parabola. So to do horizontal rectangle, I'd have to set up 3 integrals. And not only that, but for horizontal rectangles, I'd have to solve this for x, and I'd have to deal with plus or minus square roots. So I'm thinking horizontal rectangles are not the way to go. Let's go ahead and look at vertical rectangles. So with vertical rectangles, our hope is I always have the same upper and the same lower throughout the region to make it easy. Now that's not always going to be the case, but hopefully for this first one it will be. So let's go ahead and sketch in some rectangles. And it does look like for this particular region, the upper curve is always the same and the lower curve is always the same. So my area using vertical rectangles will go from, well, we'll figure out our limits of integration here in a second. We'll go from, looks like we'll start at 0 and go clear across until we get to 2. So my limits of integration go from x equals 0 to x equal 2. Now we need our upper curve minus our lower curve. So my upper curve is x squared plus 2 minus my lower curve is negative x. The incremental width of each one of these rectangles is going to be dx. And so this integral will actually be the area bounded by those two curves. Now it's not signed area, it's true area, because this is the width of the rectangle, or sorry, this is the height of the rectangle, irregardless of the fact that the x-axis is in the middle. So this is true area, it's not signed area. So x equals 0 to x equal 2. Let's simplify this a little bit. X squared plus x plus 2 dx. Now again, we're not going to focus so much on the integration here because these are skills that we should have in place. You'd go through and use the power rule, add 1, divide by the sum, and evaluate your solution with your upper point of 2 minus your lower point of 0. And in this particular case, you'll get 26/3 units squared. Now remember, this is true area. This is not signed area. It's true area. Now make sure you run through the steps to verify that 26/3 is the solution, because you'll definitely have to be able to do that. Let's go ahead and look at another area where we're looking at, again, area bounded between two graphs. Okay, for this example, we're trying to find the area bounded by the graphs of f of x equals 2 minus x squared, which is a parabola that opens down, vertex at 2 on the y-axis, and g equals x, which is a line that bisects the first and third quadrants. So let's go ahead and look at a quick curve sketch first. So we have a parabola opening down. We'll put that at 2. And then we have this line bisecting first and third quadrants. So these graphs do intersect. And I'm looking for this area right here. Now I already see that vertical rectangles will be the better one to use, because the right curve switches at this point. So I'd have to set up 2 rectangles, or 2 integrals if I used horizontal rectangles, because here the right minus left is different. The right changes, the left stays the same. So vertical rectangles are definitely the way to go, but before I can even find my vertical rectangle setup, I need to find these points of intersection. So I need to figure out what these points are in terms of x, because I'm going to use vertical rectangles. So these are my sketches of my vertical rectangles. So I need to find points of intersection. The way we find points of intersection is we set the 2 functions equal to each other. Now, both of these are in terms of x. I don't want one in terms of y and one in terms of x and try and set them equal to each other. That will not go well. So for our points of intersection, we we set these equal to each other. Moving everything to one side, I get x squared plus x minus 2 equals 0. And again, it's our hope that this factors, and this one does factor. It factors into x plus 2, x minus 1, which means my values of intersection are at x equal -2, x equal 1. And it's important that these are x values. That has meaning here. So this value is x equal -2. I don't know what the y value is. And this one is at 1. And I'm not sure what the y value is here either. And actually it doesn't even matter. The point is we're going from -2 to 1. Those are my values from A to B. Now if you wanted to find the y values, they're pretty easy for this example, because this says that the y's and the x's are equal. So I could plug them into either one, but this is definitely a little bit easier. So if I did plug them in, I'd get a 1 back and a -2 back. But the thing to remember is I'm actually interested in the x values. So let's go ahead and set up our area formula. Now again, we're using vertical rectangles, so I'm going to go from -2. I'm going to sum these rectangles from -2 to 1. So x equals -2 to x equal 1 of my upper curve minus my lower curve. Now this entire upper curve right here is this parabola 2 minus x squared that's opening down. My entire lower curve is x, the straight line x. Now a common mistake to make is to not put parentheses around this lower argument, and because this is a monomial, it doesn't matter, because the negative doesn't have to distribute through to anything. But be really careful. Always make sure that you put parentheses around that lower, so if it is more than just a monomial, it gets distributed properly. So this is my setup for area. And again, we're not going to focus so much on the integration because we already know how to do that. We're going to focus more on the setup. If you go through and integrate this, you should get 9/2 units squared. And again, I encourage you to verify how you get that solution. Okay, in our next example, we're going to be looking at some graphs that are a little bit more complicated than just plain old parabolas and straight lines. So here we're looking at to find the area bounded by f of x equal -x squared plus 10 and g of x equals 9 over x squared. Now we can go to Maple or Wolfram Alpha or something to verify what these graphs look like, and we can also use them to find points of intersection, but these are pretty straightforward graphs. The graph of 9 over x squared looks something like this. The graph of negative x squared plus 10 looks something like this. So I'm thinking their intersection looks like this, and we're trying to find these regions right here. So that's what I think is going on. So in order to figure out exactly, let's go ahead and be a little bit more careful about our graph. So negative x squared plus 10, here's a parabola opening down with its vertex at 10. So this is a graph of f of x equals negative x squared plus 10. And then we also have a graph of 9 over x squared. So this is going to come swooping in something like this. And so this is our region here that we're looking for. Now it doesn't really look like it, but these are symmetric. And I know they're symmetric because I have the same graph on either side. So if I want to, I can just find the area of, let's say, this first region, region 1, and then double it to find the total area. And I think that's what I'll do. I think that'll be a good idea. Now with this one, I can actually use horizontal or vertical rectangles. But before I decide what to do, we need to find our points of intersection. To find the points of intersection, you need to set the equations equal to each other and hopefully get a nice solution and solve. So we have negative x squared plus 10 equals 9 over x squared. We're going to multiply through by an x squared, so we get negative x to the 4th plus 10x squared plus 9 equals 0, and actually that's equal 9. And then I'm going to move everything so I have a positive leading coefficient. So x to the 4th minus 10x squared. Add the x to the 4th across, subtract the 10x squared across, plus 9 equals 0. And hopefully this will factor. X squareds look good here, minus 9 minus 1. And I get x equal plus or minus 3, x equal plus or minus 1 for my points of intersection. Now the important thing to remember here is these are values of x. So this value right here would be a negative 3 for my x. This value right here would be a positive 3 for my x. This would be a positive 1. This would be a negative 1. Now if I want to figure out what the y value is, all I would need to do is to plug in negative 3 into either one of these equations over here. If I plug negative 3 in, I get a positive 1 back out. If I plug a negative 1 in, I get a 9. If I plug a positive 1, I get a 9. And if I plug in a 3, I get a positive 1. So you can see that I have that symmetry there because I have this reflexive property across the x-axis with my y values. So let's go ahead and look at this and set up both horizontal rectangles and vertical rectangles. Horizontal rectangles on this one are definitely more work. So for horizontal rectangles, I just want to set up one integral, the one in the first quadrant, and then double my answer because I have symmetric graphs on either side of the y-axis. So I want to set up one integral, and then at the end I need to remember to double because I have symmetry. Okay, horizontal rectangles. Well, horizontal rectangles. Here's some horizontal rectangles. So when I set up my area here, my horizontal rectangles are not going to go from 3 to, what is this value? 3 to 1, because those are x values. They're going to go from 1 to 9 because those are my y values. So they're going to go from y equal 1 to y equal 9. And then when I get done, I'll have some upper minus some lower. That's going to be the length of one of these rectangles. And then the incremental width of each one of these rectangles is just a dy. So this is what my setup looks like. And technically there's brackets here. So what I need to figure out is my right minus my left. So my right curve is the parabola. So that's negative x squared plus 10. My left curve is this function that's coming toward the x-axis. That's my 9 over x squared. And we're in trouble. This function is in terms of x. This function is in terms of x, and everything has to be in terms of y. If you see your limits of integration and your incremental width of dy there, you can see that it has to be in terms of y. So what do? Well, this graph is y equal negative x squared plus 10. If I solve this for x, I get x equal, and again we'd move the negative x squared across, subtract the y, take the square root, so I'd end up with plus or minus root 10 minus y. Here I'd have y equal 9 over x squared. Solving for x squared, I get x squared equal 9 over y. Square root of both sides, I'd get x equal square root of 9, which is plus or minus 3 over root y. So I can't use these values of x. I need to rewrite this in terms of my function of y. So again, this is y equal 1 to y equal 9. Now in the first quadrant, I'm only looking at positive x values, so I'm just going to look at root 10 minus y. I don't have to worry about the negative root here because I'm only looking in the first quadrant. Now over here, this says x equal plus or minus 3 over root y, and we're using the same logic there. In this particular case, I'm only looking at the positive values of x, so I'm just going to be looking at positive 3 over root y. But remember, your curve is upper minus lower, so here I have 3 over root y. dy is the incremental width. Now, this minus sign is not here because the function is negative. This minus sign is here in order to find the length of that horizontal rectangle. So again, we're not going to focus so much on the integration techniques. This I'd have to use a u substitution. I'd let u equal 10 minus y. Du would be a negative dy, and I'd have to compensate with a negative. So go ahead and go through and verify that. And when you do, you're going to get 16/3 as a solution here. But then we need to remember to double it because I have symmetrical area. And so I get 32/3 square units for the area enclosed there. And that's using horizontal rectangles. I can also do the same problem using vertical rectangles. Vertical rectangles are easier because I don't have to go through and solve like I did up here for these values. So vertical rectangles, the area would go from, and again I'm going to find one integral and double it. Vertical rectangles, let's see if we can get rid of some of this, but I don't want to get rid of quite all of it. Okay, so my vertical rectangles would be our upper minus our lower. And we can see here that these are going to touch the x-axis if we extended them, so I know that I'm working with dx's here. Now my upper curve is the parabola, and these are going to go from 1 to 3. And I look at my x values to determine that. So x equal 1 to x equal 3. Upper is negative x squared plus 10 minus our lower, which is 9 over x squared dx. And again, technically there's a big bracket here. Base times height. Now again, I'm not going to focus so much on the integration techniques here because you should be able to verify those. But when we go through and work this, we get 16/3. And then we need to remember that we'd have to double it because I have area in the second quadrant that's equal to the same area in the first quadrant. And I get 32/3 units squared. So same answer either way. I think the vertical rectangles was definitely easier on this one because I didn't have to go through and solve for the other function. Okay, let's go ahead and look at an example of a graph that we might not necessarily know how it looks. So for this example, we're finding the area of a bounded region. We have a third-degree polynomial, that's our f of x function. And notice we have two different names for our functions. One's f and one's g, so they're a little bit easier to talk about. Now just because it's named f doesn't mean it's always upper or g is always lower. We always need to check. So here's the third-degree polynomial. G of x is the second-degree polynomial, so it's some parabola opening down. I'm not sure what these graphs look like. If we were to do a quick little curve sketch, This third degree polynomial could look something like this. And then the parabola could look something like this. They might not ever cross. Or the third degree polynomial could look something like this. And then my parabola, whoops, except this is a parabola opening down, so I better get this one right this time, could look something like this. You know, I'm just not sure what our situation is. So I think to start, you know, we could curve sketch this real quick in Maple or Wolfram Alpha. To start, I think I'd like to find our points of intersection. So let's go ahead and look at points of intersection. That'll give us an idea of what's going on here. So again, for points of intersection, you set the functions equal to each other. So I have x cubed minus 2x squared plus x minus 1 equals negative x squared plus 3x minus 1. I'm going to move everything across. So I have x cubed, and when I add the x squared across, I end up with a negative x squared. When I subtract the 3x, I end up with a minus 2x, and when I add the 1, I get 0. When you factor, you always factor out your greatest common factor first, which in this case is x, and I'm left with x squared minus x minus 2. And our hope is this trinomial will factor, and it does, x minus 2, x plus 1. So using our zero factor property, I have roots then of x equals 0, x equal 2, and x equal negative 1. So I have 3 points of intersection. So it's not this picture up here. It's probably this one or one similar to it where I cross 3 times. So I need to check and see what's going on here. It looks like to me I have 2 regions or 2 areas I'm going to find. In order to figure out what's going on, I'm just going to make a number line. This is not a slope chart or a concavity chart or anything, but it is a number line. So I have x equal negative 1, x equals 0, and x equal 2. And what I'm trying to do is I'm trying to look at these functions in these intervals and try and figure out what's going on. Who's upper, who's lower? Let's go ahead and plug in to f of x and g of x. And I'm plugging into my original functions. Again, this is not a slope chart. If you plug 1 into f, you get a negative 1 out. If you plug 1 into g, you get a positive 1 out. Okay, that tells me that my function f has a lower value on this interval. So this is my lower function from 0 to 2, and this is my upper function from 0 to 2. Now usually when we have more than one region, the upper and lower swap, but you should check just to make sure. So I'm going to plug negative 1/2 in to my f function and negative 1/2 in to the g function. It's a negative value. If I plug a negative 1/2 in to my f function, I get a negative 17 over 8. If I plug a negative 1/2 into my g function, I get a negative 11/4. Now in terms of a common denominator, that would be a negative 22/8. So this one, my f function is higher, so it's my upper, and my g function is lower, has a smaller value, so it's my lower function. And I never really know what these graphs look like for sure, but this is kind of giving me an idea of what's upper and what's lower. And this picture looks like it could be fairly correct that we have right here, but I'm not sure about these points of intersection. But notice my third degree polynomial is my upper here, and then over here my third degree polynomial is my lower. So in order to find my area here, I need to set up 2 integrals because my upper and my lower change. If my upper and lower were the same across this entire interval, I could just set up 1 integral. So my area would start out with the integral from negative 1 to 0. Well, wait a minute. Am I going to use horizontal or vertical rectangles? This one I don't have a choice. I have to use vertical rectangles because everything here is in terms of x. If I tried to solve for this and get x equals stuff only in terms of y, I couldn't do it here or here. So I'm forced to use vertical rectangles. I don't have a choice on this one. And if I'm using vertical rectangles, that means that I'm using dx's, and so I need x values. So these are x values, x equal negative 1 to x equals 0. Now from negative 1 to 0, this is the interval I'm looking at. So when I set up my integral, I need to take my upper minus my lower. Well, my upper is my f function, which was my third degree polynomial. So my third degree polynomial was x cubed minus 2x squared plus x minus 1. That's my upper. My lower was this g of x value. Now remember, we have to subtract off the entire lower, so you need to make sure you have parentheses here. Negative x squared plus 3x minus 1. And again, these are dx's because I have vertical rectangles. Now that's only part of my area. The next part of my area, I'm looking at this interval from x equals 0 to x equal 2. Now here my upper will be my parabola, negative x squared plus 3x minus 1. Our lower will be x cubed minus 2x squared plus x minus 1 dx. Like I said, we're not going to focus so much on the integration, but we'll definitely clean these up a little bit. So again, I'm going from x equal negative 1 to x equals 0. And when I combine like terms here, I end up with x cubed. And when I'm talking about this integrand right here, here I have a negative 2x squared plus an x squared is a negative x squared minus 2x dx. So that's going to give me the area of this, I think the smaller piece. I'm not sure because I don't have a clear graph here. But that will give me the area of my piece from negative 1 to 0. And again, it's not signed area, it's true area. Plus the integral from x equals 0 to x equal 2. And I combine these pieces over here, combine all my like terms. I end up with a negative x cubed plus x squared plus 2x dx. Now you might notice something pretty interesting here. Here I have a positive x cubed, here I have a negative x cubed. Negative x squared, positive x squared. Negative 2x, positive 2x. This happens because I'm just switching the order in that I subtract. Now don't look at this and think, oh, I'm going to combine my x cubes here because those will go to 0. You can't, because this function has different limits of integration on its first and its second integral. So I can't combine these terms in here. Now if you go ahead and integrate this, add 1, divide by the sum power rule, and evaluate each one of these integrals, you end up with 37/12 units squared. And again, I encourage you to go through and verify that. Okay, one last problem. Let's go ahead and find the area of the region. This one's going to be a little bit different. Bounded by the functions x equal 3 minus y squared and y equal x minus 1. Now this one, right away I can see that we need to watch out for something. First of all, in this first function I have an x equal. In this second function I have a y equal. So I probably want them both x equals, just because if I solve for y here I'll end up with square roots. So careful on this one. If I solve for x, I get x equal y plus 1. So I want to keep that in mind. Now, the graph of x equal 3 minus y squared is a parabola on its side with its vertex at 3 on the x-axis. So we'll put it out here, vertex at 3. Now the graph of y equal x minus 1, and I'm just going to put it in this form because this is how we're used to seeing it, y equal mx plus b. The slope is 1, the y-intercept is negative 1. I know if I plug a 1 in for x, it's going to cross here, and the rest of it I'm not so sure of. I'm guessing it looks something like this. So this is the region that I'm trying to find the area of, this total region right here. Now, horizontal or vertical rectangles, it's up to me. I could do either, but I notice that if I were to use horizontal rectangles, my upper and my lower curve changes. Here my upper is the parabola on its side. Here the upper is a straight line. So for vertical rectangles I'd have to set up 2 limits. So I think horizontal rectangles might be how we want to go. If you look at the horizontal rectangles, you can see that my right curve is always the parabola, my left curve is always the straight line. So I think that'll work good. We need to figure out our points of intersection. Now remember, our points of intersection that we want to find, we're interested in horizontal rectangles, so we have dy's here. So from here, points of intersection, I have to set the equations equal to each other. But this is the place we need to be careful. I can't set these two equal to each other because one's in terms of x, one's in terms of y. I need to set these two equal to each other, because remember, what we're basically saying is it's true that x equals x, and then we substitute in x equals 3 minus y squared, x equals y plus 1. I'm going to move the y squared across because I like to have positive leading coefficients. So I have y squared plus y, subtract 3, 1 minus 3 is negative 2 equals 0. And again, it's our fond hope that this will factor y plus 2, y minus 1, and I get y equal negative 2, y equal 1 for my points of intersection. Now these are y values, so this is where my y values are negative. So this is where I have a negative 2 for my y value. This is where I have a positive 1 for my y value. Now it doesn't really matter what the x values are because I don't have vertical rectangles. So I need to be really careful when I'm working here and setting these up. And again, if you want to find your x values, you would just plug your y value into this equation, y plus 1, and I get my x value. But again, it doesn't really matter. So to find my area, okay, I want to go y equals, my horizontal rectangles will start at negative 2 and go clear up to 1. And instead of upper minus lower for horizontal rectangles, I take right minus left. So my right function is the parabola, and my left function, now this is where I need to be careful, I don't want to put x minus 1 in here, I want to put y plus 1 because the incremental width of each rectangle is in terms of y, and I can't mix my variables. Rewriting this, I get y equal negative 2 to y equal 1. I end up with a negative y squared minus y. Here I'm going to have 3 minus 1 is 2 dy. And again, we're not going to focus so much on the integration. Add 1, divide by the sum, evaluate from your upper minus lower 1 to negative 2, and you'll get 9/2 units squared. And again, please go through and verify these. It's a good way to practice your integration techniques. So that's finding the area between two curves. The important things to remember are your limits of integration. You need to make sure, are they in terms of x or are they in terms of y? Am I using horizontal or vertical rectangles? If I'm using vertical, I always take my upper function minus my lower. If I'm using horizontal rectangles, I always take my right function minus my left. In the next couple lectures, we're going to be working on volume, but for now we just are working about area between curves. And if you get good at area between curves, the volume turns out to be a lot easier. Use Maple and use Maple to graph these functions. That'll kind of give you an idea what they look like, but be able to work without Maple too for some basic graphs as well. Thank you.